In this module, we shall learn about three continuous probability distribution, namely the uniform distribution, normal distribution and log normal distribution. We shall know the definition, properties and how to compute probabilities for each of these distributions. The normal distribution being the most useful and widely applied distribution in statistical theory, we shall learn in detail how to compute areas under the curve using the standard normal distribution, which is also called the Z distribution. We shall understand the concept of cumulative distribution function that helps in computing areas under the curve for given observation. We shall also know how discrete probability distribution such as binomial distribution, Poisson distribution can be approximated to the normal distribution and facilitates the applicability of these distributions for practical problems. Introduction. Now, I will give you a brief introduction of this module. We have learnt in the earlier modules that a random variable may be discrete or continuous in nature. A discrete random variable often results from counting, may take only certain finite values or countably infinite, such as number of persons entering in a shop, number of students studying in a class, number of defective items. The binomial, Poisson and the hypergeometric are few examples of discrete probability distribution. A continuous random variable, on the other hand, often results from measurement. It may take on any possible fractional value within a given range of values, such as distance travelled, depth of a lake, weight of a person. Accordingly, the probability that a continuous variable x takes a particular value, say c, is 0. That is, probability of x equals c is equal to 0, because for such variables we measure probability that x lies within an interval. We know that a probability distribution function displays all possible outcomes of an experiment along with their associated probabilities. The probability distribution function of a continuous variable, also called probability density function, denoted by PDF, function of x, is such that the probability bracket open that x is greater than a while b is greater than x bracket shut is an integration sign where the values range from a to b of function x dx, where a and b are two numbers where b is greater than a. The probability that x lies within a given interval is measured through an area that lies under the density curve. That is the graph of fx within the specified interval. The computation of this involves the use of integration technique. It must be kept in mind that unlike discrete variables, for a continuous variable, the probability within an interval does not depend on whether the lower and upper limits of the interval are included or not. This is because they are infinite possible values that x can take between the two limits. Their inclusion or exclusion will not change the probability. Therefore, the probability that x is greater than a and b is greater than x is equal to the probability that b is greater than x and x is greater than a, which is again equal to the probability that b is greater than x or x is greater than a, which is again equal to b being greater than x or x being greater than a. Given that fx is a probability function, it must satisfy the following two properties. One is that fx has to be greater or equal to 0 for all values that x can take. That is, the probability or area for any given interval is non-negative quantity. The second is that integrating an equation where the limits are from minus infinity to plus infinity of the function x dx is equal to 1. That is, the complete area under the density curve for all possible values that x can take is equal to 1. In this module, we discussed three continuous probability distribution, namely uniform distribution, normal distribution and log normal distribution. Now we will first look at uniform distribution. The uniform distribution is the simplest of all the continuous distribution. A distribution is defined to be uniform when the probabilities for all the possible outcomes are same. The density function of the continuous uniform random variable x on the interval a, b is given by f bracket open x semicolon a comma b bracket shut, then which is equal to curly bracket open 1 divided by b minus a. Here x has to be greater or equal to a and b has to be greater or equal to x. 0 otherwise. This is equation 1. Here the probability is proportional to the length of the interval under consideration. Its graph is shown by a horizontal line over the entire range of values from its lower end point A to higher end point B, whose height is equal to the probability 1 divided by B minus A. The total area under the curve can be simply calculated as the area of the rectangle A B B A, which is equal to height into width. Here the height is equal to 1 divided by B minus A, and width is the interval over which the distribution is defined, which is equal to B minus A. Therefore, area is equal to 1 divided by B minus A into B minus A, which is equal to 1 as shown in the figure. The probability that x lies within the interval, that is x lies between, is greater than c and d is greater than x, where x is greater than c, which is greater than a, while b is greater than d and d is greater than x, can be computed as the probability bracket open x is greater than equal to c and d is greater than equal to x is integration limits from c to d 1 divided by b minus a dx, which is equal to 1 b minus a integration c to d dx, which is equal to x divided by b minus a, the values from where x is equal to c and x is equal to d, which is equal to d minus c divided by b minus a. This is shown by the shaded area in the figure. Properties of uniform distribution. First, the two parameters of the distribution are its two endpoints, A and B. Second, the mean or expected value of a uniform distribution is average of the two endpoints of the distribution. That is, expected value of x is equal to mu, which is equal to a plus b divided by 2. Third, the variance of the distribution is Vx, which is equal to sigma squared, which is equal to b minus a the whole square divided by 12. Let us take an example. Suppose the time spent by each customer in a particular shopping mall during afternoon hours is uniformly distributed with A equal to 45 and B equal to 60. What is the probability of the time spent by each customer? The PDF of the distribution is written as f is a function of x is equal to 1 bracket open 160 minus 45, which is equal to 1 divided by 15, where x is greater than equal to 45 and 60 is greater than equal to x. Below that we have 0 and we have otherwise. A exceeds 50 minutes, so the probability and in bracket open where x is greater than 50 is indicated by the integral sign from 50 to 60, 1 divided by 15 dx, which is equal to x by 15, where x is equal to 50 and x is equal to 60, which is equal to 10 by 15, which is equal to 0.67. Between 45 to 50 minutes. So the probability that x lies between 50 and 45 is equal to integration 45 to 50, 1 divided by 15 dx, which is equal to x divided by 15, where x is equal to 45 and x is equal to 50, which is equal to 5 divided by 15, which is equal to 0.33. Exactly 55 minutes. The probability that x is equal to 55 is equal to the probability that x is greater than 55 and 55 is greater than x. So the integral sign is the limits from 55 to 55, 1 divided by 15 dx, which is equal to x divided by 15, where x is equal to 55 and x is equal to 55, which is equal to 0 divided by 15, which is equal to 0. Find the mean and variance of the distribution. The mean is equal to 45 plus 60 divided by 2, which is 52.5, and the variance of x is equal to 60 minus 45 the whole square divided by 12, which is equal to 18.75. Let us define cumulative distribution function fx. The cumulative distribution function CDF, denoted by fx, gives the total probability for all the values that are less than or equal to the specified value of x equal to small x in inverted commas within the defined range, that is fx is equal to the probability that small x is greater than equal to big X. It gives the probability of at most x. For a continuous random variable, it is obtained by integrating the PDF between minus infinity and the specified value of x. So fx is equal to the probability that small x is greater than equal to big X, which is equal to integration of minus infinity to x of fy dy for x which is greater than equal to minus infinity and plus infinity is greater than equal to x. It is equal to the total area under the density curve fx to the left of x as shown in the figure. Fx is a rising curve up to a maximum of 1 because the total of probability for all the possible outcomes in any experiment is 1. This is shown in the figure 2. Accordingly, the probability that a continuous variable x takes a value that lies between x1 and x2, where x2 is greater than x1, can be computed using CDF of fx. Capital X has to lie between x1 and x2. That is, the probability of x being greater than x1 and x2 being greater than x is equal to fx1 minus fx2. And the probability that capital X is greater than x2 is equal to 1 minus fx2. In the above example, calculate CDF at x is equal to 55. That is f55. We know that fx is equal to integration minus infinity to x fy dy, which is equal to integration a to x 1 divided by b minus a dy. F x is equal to 55 is equal to integration 45 to 55 fx dx, which is equal to integration of 45 to 55 1 divided by 15 dx, which is equal to x 15 from 45 to 55, which is equal to 55 minus 45 divided by 15, which is equal to 10 divided by 15, which is equal to 0.66. This is the probability that 55 is greater or equal to x. Now we will discuss the case of normal distribution. The normal distribution is considered the cornerstone of modern statistical theory. It is of considerable importance in statistical theory, especially in statistical inferences related to population parameters. It is widely used in practical problems related to height, weight, distance, production, scientific measurements, etc. Carl Friedrich Gauss, who was alive from 1777 to 1855, for the first time derived the precise mathematical formula for the normal distribution. Therefore, it is sometimes also called the Gaussian distribution. A continuous random variable x is said to have a normal distribution if its probability density function PDF is given by the following equation. Fx is equal to f x semicolon mu sigma squared, which is equal to 1 divided by sigma under root 2 pi e raised to the power of minus half in bracket x minus mu divided by sigma the whole squared. This where x small x is greater than minus in infinity and plus infinity is greater than x. This is equation 2, where mu is the mean and where mu lies between minus infinity and plus infinity. Sigma is the standard deviation and sigma has to be greater than 0. E is equal to 3.14159 and pi is equal to 2.71828, which are the two constants. Properties of normal distribution curve. The mean mu and standard deviation sigma or variance sigma squared are the two parameters of the normal distribution. The mu is the center of the distribution and sigma explains the spread of values around the center. The values of mu and sigma determine the position and shape of the distribution. It is a family of distribution where each distribution is differentiated by its combination of mu and sigma. The values of mean, that is the measure of central value, median that divides the series into two equal parts, and mode, the most frequent value, coincide. If from the peak of the distribution we draw the perpendicular on the horizontal axis, also called the variable axis, the foot of the perpendicular gives the value of the mean, median, and mode. Third, it is a unimodal distribution and the curve attains its maximum value at x equal to mu. It is a bell-shaped and a symmetric curve as shown by left-hand side figure. If the curve is folded from the middle, the two halves will coincide. The shape of the curve to the left of the mean is the mirror image of the shape to the right side of the curve. The variability of the distribution is determined by the value of sigma. The greater is its value, the higher is the spread of the distribution, and greater would be the width of the distribution. The two normal distribution curves having the same mean and different standard deviation are shown in the right hand side of the figure. We can see that both the distributions are symmetric and bell-shaped. However, observation in distribution A with higher sigma are more dispersed, therefore the curve is flattened and has thicker tails than the distribution B with lower sigma. The random variable x ranges from minus infinity to plus infinity. The tails of the curve extend to infinity in both the directions and they never touch the x-axis. This distribution being a probability density function, that is fx is greater equal to 0, and we know that the probability of a continuous random variable is given by the area under the curve. Therefore, the total area under the curve is 1. That is probability of x lying between minus infinity and plus infinity is equal to integration of minus infinity to plus infinity fx dx, which is equal to integration of minus infinity plus infinity 1 divided by sigma under root 2 pi e raised to the power of minus half x minus mu divided by sigma the whole square dx is equal to 1. Since the distribution is symmetrical about its mean value mu, this implies the area under the curve on both sides of the mean mu is 0.5. That is, probability of x greater than equal to mu is equal to the probability that mu is greater than equal to x, which is equal to 0.5. Point of inflection of the curve occurs at mu plus minus 1 sigma. It is a point where the curve changes its curvature to both of its sides. Empirically, it is observed that the approximate percentage area in the following commonly used intervals are mu plus minus 1 sigma, covers 68.27% of the total observation. That is, 68.27% of all observations lie within one standard deviation of the mean of the distribution. Similarly, mu plus minus 2 sigma covers 95.45% and mu plus minus 3 sigma covers 99.73% of the total observation as shown in the figure. If the values of mean mu and standard deviation sigma are known, the distribution is said to be fully specified. The expression used to abbreviate that x is normally distributed with mean mu and variance sigma squared is x leading to n bracket open mu sigma squared, where expected value of x is equal to mu and variance of x is equal to sigma square. Computing areas under the normal curve. In order to compute the probabilities between two x values, x1 and x2, or area covered under the curve between 2 points, we are required to use integration technique in the following manner. Probability that x is greater than equal to x1 and x2 is greater than equal to x is equal to integration of the limits from x1 to x2 function of x where mu comma sigma squared bracket close dx, that is equal to integration x1 x2 1 divided by sigma under root 2 pi e minus half bracket open x minus mu over sigma the whole square dx, which is equal to 1 divided by sigma under root 2 pi integration x1 x2 e minus half x minus mu divided by sigma the whole square dx using equation 2. The difficulty encountered in performing integral of normal density function requires tabulation of normal distribution curve areas. However, we must notice from the above equation that the area included between two values of x depends not only on the values of x1 and x2 but also on the values of the two parameters of the distribution. As the value of any one of the two parameters of the normal distribution function changes, the probability for given values of x1 and x2 would also change. This means we would require as many tables as the number of possible combinations of mu and sigma squares. Since there can be infinite combination, it is not practicable to prepare table for each of the possible combinations. To deal with this, we transform each normal random variable with a specified mu and sigma squared into a standard normal random variable called the z variable, which has 0 mean and 1 standard deviation or variance. This standardized variable is used to calculate the probabilities of all normal distributions irrespective of the values of mu and sigma squared, converting normal variable into standard normal variable. The distribution of any normal random variable with mean 0 and variance 1 is called a standard normal variable. The normal random variable x is converted into z using the following conversion formula. Z is equal to x minus mu divided by sigma, where as mu is equal to expected value of x and sigma is standard deviation x. Using rules of expectation, we find the two parameters of the standard normal variable z. The mean and standard deviations are 0 and 1 respectively. Expected value of z is equal to expected value bracket open x minus mu divided by sigma, which is equal to ex minus mu divided by sigma, which is equal to mu minus mu divided by sigma, which is equal to 0. Vz is equal to v bracket open x minus mu divided by sigma, which is equal to vx divided by sigma squared, which is equal to sigma squared divided by sigma squared, which is equal to 1. Replacing x with the z variable, equation 2 can be rewritten as function of z is equal to function of z semicolon 0 comma 1 bracket shut is equal to 1 divided by 2 pi under root e raised to the power of minus half z squared, where z lies between minus infinity and plus infinity and e and pi are two constants. Properties of z distribution are similar to those of normal distribution. That is, the random variable z has an infinite range. That is, z lies between minus infinity and plus infinity. The standard normal curve is also a bell shaped with mean, median, and mode coinciding at 0. The z curve is centered at its mean value 0 and is symmetrical around it. That is, z lies between is greater than equal to minus infinity and 0 is greater than equal to z. Probability that z is greater than equal to minus infinity and that 0 is greater than equal to z is equal to the probability that 0 is greater than equal to z, which is equal to the probability that z is greater than equal to 0 and plus infinity is greater than equal to z, which is equal to the probability that z is greater than equal to 0, which is 0.5. Its point of inflection occurs at plus minus 1. It should be noticed here that for the normal distribution, it occurs at mu plus minus 1 sigma. For z curve, since mu is equal to 0 and sigma is equal to 1, therefore 0 plus minus 1 into 1 is equal to plus minus 1. The respective limits of z covering 68.27%, 95.45% and 99.73% of area under the standard normal distribution curve are plus minus 1, plus minus 2 and plus minus 3. We can transform the two values x1 and x2 into z1 and z2, which are defined as x1 minus mu divided by sigma and x2 minus mu divided by sigma respectively, and compute the area between these 2 points. The probability that x is greater than equal to x1 and that x2 is greater than equal to x is equal to the probability that z is greater than equal to z1 and z2 is greater than equal to z, which is equal to integration z1 to z2 1 over sigma root 2 pi e minus half z squared dz, which is equal to 1 divided by sigma under root 2 pi integration from z1 to z2 e raised to the power of minus half z squared dz. In fact, converting x variable to z variable, we are changing the scale of measurement on the horizontal axis. Suppose given x is normally distributed with mean 100 and standard deviation 50. When x is equal to 100, z is equal to 100 minus 100 divided by 50, which is equal to 0. And when x is equal to 150, z is equal to 150 minus 100 divided by 50, which is equal to 1. And for x equal to 50, z is equal to 50 minus 100 divided by 50, which is equal to minus 1. Similarly, for other x values, we can calculate corresponding z values as shown in the figure. Using standard normal distribution table to compute probabilities. To compute the probability, we make use of standard normal variable tables attached at the end of the module. The standard normal distribution table is given in the form of cumulative distribution function CDF, which is denoted by phi z. We know that CDF of z is defined as the probability of small z being greater than equal to big Z is equal to integration minus infinity to z a function of y semicolon 0 comma 1 dy. For any given normal distribution, firstly we convert x into z variable and compute probabilities using the CDF table of the standard normal variable. Making use of CDF of z, we can write the probability that x is greater than equal to x1 and that x2 is greater than equal to x is equal to the probability that z is greater than equal to z1 and that z2 is greater than equal to z, which is equal to phi z2 minus phi z1, which is the required probability. Students should bear in mind that since we are studying continuous variables, the sign less than, greater than equal to, less than equal to can be used interchangeably. Let us take an example. It is known that on an average, students spend 600 hours to learn a program with standard deviation of 100 hours. Assuming normal distribution, find the probability that to complete the program, a student selected at random will take A more than 735 hours, B between 500 to 700 hours, C less than 550 hours. Solution. To find these probabilities, first we need to convert x into the z variable. When x is equal to 735, z is equal to 735 minus 600 divided by 100, which is 1.35. More than 735 hours, that is the probability that x is greater than 735 is equal to the probability that 1.35 is less than z or that z is greater than 1.35. Since the standard normal variable table is in the CDF form, which directly gives probability of z less than or equal to 1.35, that is the probability that 1.35 is greater than z. Therefore, to compute, we proceed as follows. The probability that z is greater than 1.35 is equal to 1 minus p, which is the probability of 1.35 being greater than z, which is equal to 1 minus phi in brackets 1.35. Further, we know that 1.35 is equal to 1.3 plus 0.05. We look at the intersection of the row corresponding to z is equal to 1.3 and column that corresponds to 0.05. The corresponding cell gives probability which is equal to 0.9115, which gives the probability that 1.35 is greater than z is equal to phi 1.35. Therefore, the probability that z is greater than 1.35 is equal to 1 minus the probability of 1.35 being greater than z, which is equal to 1 minus phi in brackets 1.35, which is equal to 1 minus 0.9115, which is equal to 0.0885. Between 500 to 700 hours, the probability that x is greater than 500 and 700 is greater than x. Since when x1 is equal to 500, z1 is equal to 500 minus 600 divided by 100, which is equal to minus 1.0. And for x2 is equal to 700, z2 is equal to 700 minus 600 divided by 100, which is equal to plus 1. Thus, the probability that x lies between 700 and 500 is equal to the probability that z lies between 1 and z is greater than minus 1. Also, we know with CDF fx, we know that x has to lie between a and b. We know that the probability that x lies between a and b is equal to fb minus fa. Again, this means that the probability that z lies between plus 1 and minus 1 is equal to phi 1 minus phi minus 1, which is equal to 0.8413 minus 0.1587, which is equal to 0.6826. This also confirms the 10th property of the normal distribution, that mu plus minus 1 sigma is equal to 0 plus minus 1 into 1, which is equal to plus minus 1, covers approximately 68.27 of the total observation. C less than 550 hours, that the probability that 550 is greater than x, when x is equal to 550, z is equal to 550 minus 600 divided by 100, which is minus 0.5. Thus, the probability that 550 is greater than x is equal to the probability that minus 0.5 is greater than z, which is equal to phi minus 0.5, which is equal to 0.3085. Now we will consider the application of normal distribution. The normal distribution is a continuous probability distribution, yet it is often widely applied to obtain probabilities for discrete distribution. However, in such cases, some corrections are to be made to ensure that probabilities are computed correctly. Normal distribution approximation to binomial distribution. It has been observed empirically that the normal distribution provides a very good approximation to the binomial distribution. One, if the number of trials n is large and the probability of success p is not very close to 0 or 1. Second, and also for small n, provided p is reasonably close to 0.5. To ascertain this for a given binomial distribution, b bracket open x semicolon n comma p. Firstly, we draw a histogram with binomial probabilities with the given n and p. Here we know that expected value of x is equal to mean mu and variance of x is equal to variance sigma squared of the binomial random variable are np and np bracket open 1 minus p, which is equal to npq respectively. Using the same parameters, we superimpose the normal curve on the binomial probability histogram and find how well it fits as shown in the figure. If it provides a good approximation, we can compute the probabilities using standard normal distribution table. To generalize, if x is a binomial random variable with mu equal to np and sigma squared equal to np, 1 minus p is equal to npq, then as n tends towards infinity, then z is equal to x minus np divided by under root npq can be approximated by the standard normal distribution where f is equal to z semicolon 0 comma 1. While computing binomial probability using the standard normal distribution, since a discrete variable is approximated by a continuous variable, a minor adjustment called continuity correction is made. Using binomial distribution, we know that the probability that small x is greater than equal to capital X is sigma kx equal to 0, b k semicolon np. This is approximated by the area under the normal curve to the left of x plus 0.5 instead of x. Therefore, the probability that small x is greater than equal to capital X is the probability bracket open whereby x plus 0.5 minus np divided by under root npq is greater than equal to z. For example, suppose given n is equal to 25, p is equal to 0.6, and then mu is equal to np, which is equal to 24 into 0.4, which is equal to 15, and sigma squared is equal to npq, which is equal to 25 into 0.6 into 0.4, which is equal to 6, and standard deviation of x is equal to under root npq, which is equal to 2.5. 2.45. Then probability of x is equal to 10 is equal to the probability that 10 is greater than equal to x minus the probability that 9 is greater than equal to x, which is equal to b bracket open 10 semicolon 25 comma 0.6 minus b 9 semicolon 25 comma 0.6, which is equal to 0.034 minus 0.013, which is equal to 0.021. Approximating the same with area under the normal curve, the probability of x equal to 10 is equal to the probability that x lies between 10.5 and 9.5, which is equal to the probability of 9.5 minus 15 divided by 2.45, and that z has to lie between this and 10.5 minus 15 divided by 2.45. That is equal to that z is greater than equal to minus 2.25, and that minus 1.84 is greater than equal to z, which is equal to phi in bracket open minus 1.84 minus phi in bracket minus 2.25, which is equal to 0.0329 minus 0.0122, which is equal to 0.0207, which approximates to 0.021. Generally speaking, if the binomial probability is not too skewed, the normal distribution provides a good approximation. In practice, if both NP and N1 minus P are greater than equal to 10, the approximation is considered to be acceptable. Normal distribution approximation to Poisson distribution. Similar to the binomial distribution, Poisson distribution can also be approximated by the normal distribution under some conditions. We know if a random variable x follows a Poisson distribution with parameter lambda, then its probability function is probability of x lambda, which is equal to e raised to the power of minus lambda, lambda x divided by x factorial. That is where x is from 0, 1, 2, etc. The Poisson distribution has only one parameter lambda, where expected value of x is equal to lambda, which is equal to Vx, and standard deviation of x is equal to root lambda. As the value of parameter lambda increases, Poisson distribution can be approximated by the normal distribution with mean and variance equal to lambda. Thus, z is equal to x minus lambda divided by root lambda can be approximated by the standard normal distribution with 0 mean and 1 variance. That is f bracket z semicolon 0, 1. The Poisson random variable also requires continuity correction. For example, in a large manufacturing unit, on average, on a given day, 15 workers remain absent from their work on account of illnesses and other reasons. Assuming Poisson distribution, compute the probability that on a given day, 19 or less workers will be absent from the work. Solution. Firstly, we use the Poisson distribution to calculate the exact probability. Using the Poisson table with lambda equal to 15, we get the probability that 19 is greater than equal to x, which is equal to f19 comma 15, which is equal to 0.875. Now, using the normal approximation with continuity correction to the Poisson distribution, we obtain the probability that 19 is greater than equal to x is equal to the probability that 19.5 is greater than equal to x, which is equal to the probability that 19.5 minus 15 divided by root 15 is greater than equal to z, which is equal to the probability that 19.5 minus 15 divided by 3.873 is greater than equal to z, which is equal to the probability that 1.16 is greater than equal to z, which is equal to phi 1.16, which is equal to 0.8770, which is same as the exact probability calculated from Poisson tables. Lastly, we discuss the case of log normal distribution. A continuous random variable x has a log normal distribution if limit x has the normal distribution with parameters mu and standard deviation sigma. The PDF of the log normal distribution is given by bracket open 1 divided by sigma under root 2 pi e raised to the power of minus half limit x minus mu divided by sigma the whole squared, where x is greater than equal to 0 and 0 where mu and sigma squared are mean and variance of ln x, and e and pi have the same meaning as in the normal distribution PDF given above. We can also understand log normal distribution as x is equal to e raised to the power of y, where y is equal to ln x, where y is normally distributed with mean mu and standard deviation sigma. Properties of log normal distribution. The parameters mu and sigma squares are commonly called the location and scale parameters respectively. The normal distribution is symmetric in its shape, but log normal distribution is positively skewed. Figure depicts different shapes of the distribution corresponding to various values of mu and sigma squared. As the value of x increases, the function of x first increases, reaches its maximum, and then decreases. The function of x tends to 0 as x tends to infinity or to 0. The mode of the function occurs when x is equal to e raised to the power of mu minus sigma squared. The mean and variance of x in log normal distribution function are a into expected value of x, which is equal to mu, which is equal to e raised to the power of mu plus sigma squared by 2, and vx is equal to e raised to the power of 2 mu plus sigma squared e sigma squared minus 1, which is equal to e squared mu plus sigma squared minus e 2 mu plus sigma squared. Here ln x has a normal distribution. Therefore, the standard normal variable z is defined as equal to ln x minus mu divided by sigma. The CDF of log normal is given by f bracket x mu sigma, which is the probability that small x is greater than equal to x, which is equal to the probability bracket open limit x, which is greater than equal to limit small x, which is equal to the probability that limit of x minus mu divided by sigma is greater than equal to z, which is equal to phi in bracket limit x minus mu divided by sigma, whereby x is greater than equal to 0. For example, suppose the life of a remote control used measured in thousands of hours for electronic appliances has an approximately log normal distribution with mean equal to 2 and sigma equal to 1. Find the probability that the life of the remote control is between 2 and 4, second exceeds 6, third, find the mean and variance if mean is equal to 3 and sigma equal to 2. Solution between 2 and 4. The probability that 4 is greater than equal to x and that x is greater than equal to 2 is equal to the probability bracket open of log 2, which is less than equal to log x, which is further less than equal to log 4 bracket closed, which is equal to the probability bracket open 0.6931, which is less than equal to log x, which is less than equal to 1.3863, which is equal to the probability that z is greater than equal to 0.6931 minus 2 divided by 1, and 1.3863 minus 2 divided by 1 is greater than equal to z bracket closed, which is equal to the probability that z is greater than equal to minus 1.3069 and that minus 0.6137 is greater than equal to z, which is equal to phi bracket open minus 0.61 minus phi bracket open minus 1.31, which is equal to 0.2709 minus 0.0951, which is equal to 0.1758. The probability that x is greater than equal to 6 is equal to the probability bracket open log x, which is greater than equal to log 6, which is bracket shut, which is equal to probability of log x, which is greater than equal to 1.7918 bracket shut, which is probability bracket open z is greater than equal to 1.7918 minus 2 divided by 1 bracket closed, which is equal to the probability that z is greater than equal to minus 0.2082, which is equal to 1 minus phi bracket open minus 0.21 bracket closed, which is equal to 1 minus 0.4168, which is equal to 0.5832. C. Find the mean and variance if mean is equal to 3 and sigma equal to 2. We know expected value of x is equal to mu, which is equal to e raised to the power of mu plus sigma squared divided by 2, which is equal to e raised to the power of 3 plus 2 divided by 2, which is equal to e raised to the power of 8 divided by 2, which is equal to e raised to the power of 4. And Vx is equal to e raised to the power of 2 mu plus sigma squared into e raised to the power of sigma squared minus 1, which is equal to e raised to the power of 2 bracket open mu plus sigma squared minus e raised to the power of 2 mu plus sigma squared, which is equal to e 2 raised to the power of 2 bracket open 3 plus 2 minus e raised to the power of 2 into 3 plus 2, which is equal to e raised to the power of 10 minus e raised to the power of 8. Let's summarize the discussion we have done so far. The continuous distribution functions are used when the random variable under consideration can take any value lying within a given interval. The uniform, normal and log normal are the three commonly used continuous distribution that we have learnt in this module. The uniform distribution is applied when the probability for all possible outcomes is same. The lower and upper endpoints over which the distribution is defined are the two parameters of this distribution function. The normal distribution is the most important of all continuous distribution, and it is widely applied in problems relating to height, weight, test score, yields and in scientific measurements. Then third, it is symmetric, bell-shaped, single-peaked distribution that extends indefinitely in both directions. The mean and its variance are the two parameters of this distribution. On account of difficulty in computing the area probability using integration technique, each normal distribution is transformed into a standard normal distribution, which is called the Z distribution, and standard normal tables are used to compute the required probability. The normal distribution also finds enormous application as a limiting distribution of various discrete probability distributions such as binomial and Poisson distribution. The log normal distribution is different from normal distribution in the sense that the random variable is limit x and not x. It is positively skewed and is defined only for those random variables that can take non-negative values.